Uh, okay, so now let's continue our discussion on these second order linear PDEs. And I want to come back after defining these three types of equations, hyperbolic, parabolic, and elliptic. I want to come back to the standard model equations that we introduced at the beginning of the course, and now examine their characteristics and see what are the type of those equations. Okay, those standard model equations that we talked about. So we have introduced three canonical initial boundary value problems. Okay, so we introduced these three canonical problems. So, and what are they? So the first one is, and let me do it with this, is second order wave equation. Okay, so the equation that we had for this one was partial square u over partial t squared minus beta square partial square u over partial x square equals to 0. Okay, so now let's see what are these coefficients here for this problem, right? So if you remember, this was our general second order PDE, right? And so now we want to see what are these equations. The first one is for t or x t. The second one is xt. Third, x squared tx. Okay. So I want to see what are a, b, c, d, e in this equation. So a is what? Is 1, right? How about b? Do we have anything partial or partial x, partial t? No. So it's going to be 0. And c is minus beta square, right? So this is going to give me b square minus ac equals to beta square, right? And this is greater than 0. So if you remember, if b squared minus ac is greater than 0, then we have hyperbolic solution, and we're going to have two real characteristics. So this tells me that the solution is hyperbolic. This is the type of this equation is hyperbolic, and we are going to have two real characteristics, and they are going to be dx over dt, because b is 0, so we are going to have plus minus, and a is 1, beta, right? Based on this one here, you're gonna have plus minus beta. Okay, so let me draw these characteristics quickly so you get more insights into how does this look like. Okay, let me do it here. This is the boundary. So we have x here, and then here we have t, and here we are at x equals to L, and this is gonna be, let me draw some of the characteristic lines. So let's do this one. Let's do it with orange. So this can be dx over dt of beta. And then the other one, I'm gonna draw it with, say, this color. So this is gonna be minus beta. So let me just do this one, because we don't have space. Okay. So these are gonna be the characteristics. This one, the slope of it is gonna be 1 over beta. And here we have a right boundary condition here. So we have one boundary condition here. And then we have another boundary condition here. And at the bottom, we have two initial conditions, right? So here we have two initial conditions, right? Because it's at t equals to 0. And for example, it could be u, use one for example, u is u0x, right? And the other one can be like for the gradient of that, du over dt equals to u1x, right? So two initial conditions. And then we have one boundary condition at the left and one at the right. Okay. So I want to give you an overall idea about this domain of dependence for this problem, that where in the space you need boundary condition in your solution space or initial condition to be able to solve this problem. Okay, so a general view of that, if you have, let me just draw it quickly. If this is x, here is L, and this is T. So we can have two sorts of solution here. So one, this is gonna be one characteristic that we have. So I'm gonna draw it like this. And then the other characteristic can be something like, say, this one. It's a negative slope. Okay. So now we have four regions here. Okay. So the first region, I'm gonna show it with A here. Then we have the second region, B, third region, C, and then we have the fourth one, D. Okay, so at A, as it is clear from here, so at A, you need two initial conditions, right? So at this region, you need two initial conditions to be able to find the solution. Okay, so let me do it with this maybe. Okay, so at A you need two initial conditions. Then let's investigate B. So at B, what do you need? Here, for example, if you are a point here, you need if you continue the characteristics, you're going to get something like this, right? So you will need one initial condition from here and one left boundary condition from here. So you need left boundary condition plus one initial condition. So C is gonna be similar, but now you need a right boundary condition plus one initial condition. Okay, so if you draw it here, for example, for 1 point, you need initial condition from here and one boundary condition from here. Okay. And at D, you only need two boundary conditions. So if you are here, you only need the boundary conditions that are coming from these sides. Okay, so this is the domain of dependence for these type of equation. In general form, that what information you need to be able to solve this hyperbolic second order wave equation. Okay, so just one note here that as you see, you need both boundary condition and initial condition for solving this problem, right? So this problem is what we call initial, which it means you need initial condition, and boundary, because the problem is also dependent on the boundaries, value problem. Okay, so we call this initial boundary value problem, or IBVP. And this problem arises in dynamic problems, right? When you have a system that is dynamic. For example, waves and vibration, right? These dynamic problems, this is where this problem arises, second order wave equation. Okay, so let's go to the second canonical problem, or standard model equation that we investigated. So the second one is heat equation. So let's see the heat equation. Let me write it with the same color. Heat equation. So let's see what it is. So partial u partial t, if you remember from what we talked about, minus d partial square u over partial x is square equals to 0. So now let's examine what are the coefficients for this equation. So a here is what? Do we have any partial square u over partial t square? No, right? So it's gonna be 0. B, what is b? It is 0, right? We don't have the second component, and only c is gonna be minus d here. So b squared minus ac is gonna be 0, and so we are in this regime, right? So this is gonna be a parabolic equation based on this classification that we made. So this is gonna be parabolic equation, and this means that we have only one real characteristic, and the characteristic is gonna be, if we do a trick, it's gonna be dt over, if we write dt over dx instead of dx over dt, this equals to a over minus b plus minus square root of b squared minus ac, right? Here you have it, right? So if you just write it reverse, you are gonna get that equation. So this is gonna be 0 here, right? And I did this because dx over dt is gonna be infinity. So dt over dx is gonna be 0. So now let's see the characteristics in this equation, the domain of dependence and how they look like. Okay, so let me draw it here. Okay, so this is x, this is x equals to L, this is x equals to 0, and let me now draw the characteristics. So the characteristic curves. So the characteristics are gonna look like something like this. Right, because dt over dx is gonna be 0. So this is gonna be the characteristic, and we are gonna also have the initial conditions which are gonna propagate in time like this, and these are different than the characteristics. Okay, so let me now show this. So this is one characteristic with c equals to infinity, and then on the right here we have one boundary condition. At the left we also have one boundary condition, and then at the bottom here we had two initial conditions, but here we only have one initial condition. Okay, so this is the difference with the second order wave equation. Okay, so this is what we call heat equation. Okay, so as you see again from the domain of dependence, the solution of this PDE also depends on initial and boundary values. So this is also, we call this to be again an initial and boundary value problem. Okay, so this is also initial and boundary value problem, or IPVP. And this problem arises again in dynamic problems, this equation. And examples of that can be, for example, heat flows, right? This is a heat transfer problem. So in heat transfer, this is a very important problem, this equation, right? So this is the diffusion of heat and transfer. Okay, so now let me go to the third type of equation, canonical model that we talked about, and that is Laplace equation. Okay, so Laplace equation, the formula for that is partial u over partial x square plus partial square u over partial y square equals to 0. So what are the coefficients here? So if we just assume x is t and y is x, or vice versa here in this equation, right? Then a is going to be 1, b is going to be 0 because we don't have partial over partial x over partial t, and c is going to be what? 1. Right? So this is going to give me a equals to 1, b equals to 0, and c equals to 1. So b squared minus ac is gonna be minus 1, which is less than 0. And so this equation, based on this definition that we had here, is gonna be elliptic, and we don't have any real characteristic for this equation. Okay, so this is gonna be elliptic, and no real characteristic. So it does not propagate, and the boundary conditions here are reflected everywhere in the solution. Okay, so let me draw it so you understand this better, because this doesn't have any characteristics, right? So it's not like previous problems where we had and so doesn't have a similar behavior. So it can be anything if you have this domain, right? So let me say this is x, this is t, and this is your domain of solution, like where you are seeking your solution. And so you have to solve this uxx plus uyy equals to 0 over this domain. And the only and the boundary conditions are going to be reflected everywhere here, right? So in the whole domain they are going to be reflected. So there is no real characteristics here like the previous cases. So let me show it here. So if this is your boundary condition, say any boundary condition, then for example you can define it you can define a condition over that boundary condition. Okay, so for example you can say u over the perimeter of this boundary that I define should be 0, right? So this can be a boundary condition that you define, and then you can solve this equation, so based on that boundary condition that you defined. Okay. So as you see, this problem does not depend on initial condition, and this is therefore a pure boundary value problem. Unlike the other ones, so this is only pure boundary value problem, or BVP. We don't have any initial condition, and this problem arises, as you see, it's not time dependent, right? So it only arises in static problems. For example, electromagnetic, magnetics, or steady solutions of some equations. Okay, so this is the end of this classification of PDEs and 3 important canonical PDEs that we have. So if you remember, I want to just go to a very brief review of this. So we started with a general form of linear PDEs, second order linear PDEs, and then we found the characteristics, curves in this general form that is shown here from this by converting this PDE into a system of linear first order PDEs, and then we define these hyperbolic, parabolic, and elliptic type of equations based on the characteristic values. And after that, we started to classify those 3 canonical initial boundary value problems that we had discussed. Second order wave equation, which, as you see, is a hyperbolic equation, and we talked about the domain of the Pdes in this. Heat equation, which is a parabolic equation, and it only has one characteristic, and it's a initial boundary value problem. And lastly, we talked about Laplace equation, which is an elliptic equation, elliptic type, and the boundaries conditions are reflected everywhere in the solution of this domain. And this one is a pure boundary value problem. Okay, everyone, thank you very much and have a nice weekend.